My name is Anna Oprea. I am the European lead of the Vulnerability Coordination Center. This is the group at Google that is responsible for providing coordinated response for vulnerabilities or important issues that affect a lot of Google products. So if you've seen the bug bounty presentation or what the heck yesterday, some of the vulnerabilities that researchers discover might end up on my team's plate to basically coordinate and make sure that all the Google products are secure, safe, and trustworthy for our users. I've been at Google for the past 8 years. I've been working at the intersection of software development, reliability, and security. And I've started my career a decade and a half ago as a sysadmin, worked as a software developer in technical consulting, also have lived in Romania, where I'm originally from, in France and in Germany. So I try to find the common approach, both across cultures and across technologies. Today, I want to talk to you about security by design. Well, we all know as developers that security and reliability are important properties to build in our products. But how secure and how reliable should our products be? 100% would be a great target, but I'd like to argue that's never the target that you should be aiming for. That's more security and more reliability than is possible unless you unplug the computers and disconnect them from the internet. It's also generally not what customers want or need. So my suggestion is to try to map the level of risk that the business is willing to take to the features that your product is providing. So that's what we're going to talk about today. We're going to discuss some common properties of security and reliability, as well as ways in which they differ. We are going to discuss managing security and reliability risk, and we'll take a deep dive into designing for least privilege with a few best practices and key components that hopefully will help you and your organization, depending on what stage of maturity you are in, to learn from and adapt. We'll call out a few other design strategies apart from least privilege. There's a lot. Then I'm sure that there can be many follow-up presentations to learn about. And we'll wrap up by hopefully convincing you to shift security and reliability left. Security and reliability. Like I mentioned, they have many common properties. Security and reliability are not features, are not something that your customers will be asking you for, or that is slowly starting to change. I think customers are asking for more security and reliability right now. But they are not the shiny new button that they will click, the new functionality that your product will have. They are emergent properties. They are requiring constant attention. They require testing because they will be a result of the many ways that the different parts of your product are interacting. And in today's modern software architecture, the systems are very complex. So ways in which different parts are interacting might have effects on security and reliability. So if you're making a change related to a feature, it might result potentially in an outage. It might have security flaw that you were not expecting, and then the whole rollout process and everything might require changing. So let me start with a story to tell you about the different common properties that security and reliability have. In 2012, in September, Google had announced a change in the wireless password of the on the buses that connect the Bay Area campuses. You might know that Google has the headquarters in Mountain View. So the team responsible for transport emailed the many thousands of Googlers working in that area at that time and told them, please check out the password manager, which is where Google stores third-party passwords to check the new password for Wi-Fi. Of course, they didn't send it in plain text by email. So everybody started trying to connect to the password manager to figure out what the new Wi-Fi password is. People wanted to work on they're called G-buses to the office. It was before the times of when home office was possible. So when many thousands or tens of thousands of network connections came in at the same time to the poor password manager created 5 years back for dozen or most hundreds of system administrators, what do you think happened? The password manager went down. So an engineer was paged. The engineer was on the east coast of the US and had opened playbook with instructions, like a set of procedures that they are supposed to follow to deal with the outage. There was never an outage before in the 5 years of existence of the software, so other than reading the procedures, they had no idea what to do. Thankfully, the procedures were up to date, and they had the right permissions to do everything. However, they required a step that the engineer was not able to do themselves, which is to take a card from a hardware module, from an HSM, and restart the system. That card was not on the east coast of the US, where the engineer was located, but in Australia and in the Bay Area. The engineers in Australia were still awake and could access the safe, but the safe in which the card was required a PIN. And where do you think the PIN for the safe was? In the password manager that was right now offline. So they waited for the engineers in Mountain View to come online, and they actually knew the password by heart, so they could access the card. And they could insert it in the HSM so that it restarts. However, the system did not restart. It had a cryptic error saying something like, could not restart, problem with card, something like that. And in the meantime, the colleagues in Sydney had gotten powered rails and actually managed to access the safe. That's an interesting story in itself, but we'll let that aside. They also inserted the card in the HSM and had the same error. Another hour passed by and they figured out that the little green blinking lights did not actually mean that the cards were inserted correctly. They needed to be turned around, and then the password manager restarted and the outage was over. So, security and reliability. They are invisible until something happens. There were no previous outages of the password manager, so it was almost 100% reliable until this happened. So it's an invisible system. It requires constant assessment. There were no tests previously done. What happens, or regularly done, what happens if the password manager is offline. And systems require, systems evolve, so also the security and reliability properties need to be regularly tested. However, there are different design considerations to be taken into account. Basically, the issue that affected the password manager was a reliability issue. It actually had poor load balancing and load shedding capabilities. This was changed after the outage. And this properties that wanted to make the system more secure actually made it harder to fix. So we need to be careful when making assessments of security and reliability, which is the next topic I'd like to touch on, managing security risk. There are many different forces that are trying to affect your products from the security perspective. So the most important way to approach the problem is to look at the humans behind. So basically understand what actors are trying to detect what's happening in your organization, and if there's any benefits that they can take out of that, what their roles are, and what actions they could perform. Your company might not realize that they are a target, and the motives of the adversaries are very, very varied. So if we go back to the people part, historically, the first people that were called hackers were those that were enthusiastic about computers, wanted to learn how they work, and try to improve them. These days, there are security researchers who are looking for flaws in products and report them responsibly. And that's where your company can benefit a lot in, for example, having bug bounty programs. However, particularly on the reliability side, many issues might come from simple flaws, copy-paste away that is not properly checked or not properly modified from a procedures book might actually result in an outage, or an insider that may be dissatisfied with their performance review might look into adding backdoor so that they can change something. So all of these might have effects on both the security and the reliability of your product. On the security risk side, particularly from a threat analysis perspective, a few things to consider are that you might not realize you're a target. For example, Adobe, a company known particularly for the software used for, created for content creators, was attacked in the past, and the attackers actually successfully managed to get the signing certificates with which they could sign their malware. They used basically the company just for distribution of malware. You should start with the basics. You might actually think that you should look for a very complex attack scenarios, but a lot of attacks come from phishing. A lot of successful attacks come from phishing. So look at ways in which your employees are trained and know that they shouldn't be clicking on any weird links that come over email, and the phishing attacks are actually quite sophisticated these days. You shouldn't underestimate your adversary. On the other end of starting with the basics are state actors. So I think you might have heard, for example, that the NSA was managing to take Cisco routers and basically install backdoors in them so that they could track particular organizations that they wanted to monitor. Attribution is hard, and maybe not the most important part that you're looking at. An example that is particularly probably relevant today, but that's in the first time that we were discussing this, we would not have detected the importance of that, is NotPetya. There was, I believe in 2015, a malware that was distributed across the world, ransomware, with the purpose of getting basically money. It was financially motivated from the victims in order for them to get back their data. A year later, there was malware distributed that was called NotPetya, which was distributed through the financial software used for particularly tax in Ukraine. And although it was very similar in the way it acted, it looked like it might have been created in order to reach the Ukrainian population. So rather than looking at who might have created an, in order to look at what actors and what roles are looking for you as a target, rather than looking at who those people are. Maybe make sure that you understand their tactics, techniques, and procedures, or TTPs. Attackers aren't always afraid of being caught, particularly internationally. And if we're looking at the more sophisticated attacks, even if you do manage to figure out who an attacker is, that might be still not. It might still not be possible to get them because of international crime follow-ups. So we talked a little bit about threat modeling and security risk. In relation to that, we are going to talk a little bit about how to manage reliability risk. And here we have a tool that's been, I think, used successfully for probably close to a decade now. Christoph talked yesterday about what we learned from production. So error budgets. Error budgets are the way in which you monitor customer happiness. What is important is that your customers are happy. That's when they're going to use your product. They are going to be referring it to their friends. They're going to be referring it to their partners, and they will not be keeping your support teams busy. So we have these SLOs, or service level objectives, that all stakeholders in the organizations need to approve. And above this threshold, all your customers should be happy. And under it, if something happens, then you would notice that your support teams are getting more reports and so on. So basically, we have a budget of unreliability, which is the difference between 100% and this target that you're aiming to define. So to have an example of error budget, let's look at Bigtable. This is one of Google's large-scale distributed systems. And there are customers that serve data directly from Bigtable. This means that the requests are in the user path, so it needs to be low latency and have high reliability. On the other hand, we also use Bigtable for large-scale offline analysis. So in such a situation, we want to have large throughput, but the reliability of it doesn't need to be high. Like if one operation cannot succeed, it can be retried, and generally it takes quite a long time. So the risk tolerance is very distinct for these two parts of one system, of one complex system. Basically, if we look at what success means from the one implementation standpoint, which are the queues, then the definition of success will be antithetic between these two examples. For the user request, then we want the queues to always be empty. So we want to serve requests very fast, but from the repository to perform online analysis, we want the queues to be always full so that there will always be something new that is being processed. So the way to solve the problem of how do we define SLOs for such a product is to actually have multiple SLOs. So the way Google has solved this problem is to basically implement data centers where there are computers focused on low latency and high reliability. And there are other data centers, or maybe separate parts of the same data center, where we've serve the offline analysis customers. So since we had a short look at how to manage security and reliability risk, security risks through threat modeling, and reliability risk through error budgets, let's have a deep dive on designing for least privilege. So basically, if you were to be evil, if your company upset you, what could you do? How would you do it? Would you be able to cover your tracks? Basically, this is one of the models to which we want to look at how can we design our products so that they are secure and reliable. And leaving the evil part aside, people make mistakes. We all make mistakes. So we might be just copy-paste fail away from basically worsening an outage that we're trying to respond to. So let's look at a few best practices for this privilege. The first one is small functional APIs. What do we mean by APIs? Basically, any interaction that will modify the state of a system. The Unix philosophy talks about do one thing really well. And this philosophy from the 70s might ring more true today than ever, although we might want to adapt it to actually APIs. We're talking about functional because it is very difficult to monitor and apply this privilege to interactive APIs. So for example, if an attacker might penetrate your network and reach a system where they can run commands, they might not actually run the scripts that they want to run from the shell, but they might do that, for example, from an editor or from an interactive editor like Vim. So detection for something like this is complex and more expensive. It is possible, but you might have an easier time if you basically design your APIs to be not interactive. Small, because if you have a large attack surface, then you also have a large surface that you want to protect. So looking at the POSIX API as an example, where users are looking at basically updating systems, performing changes, adding users, and all of that. There are a lot of functionalities that were built there. So if you want to make sure that you add protections in place for what users can or should be able to do and what they should not be able to do, then there's a lot of edge cases that you need to look at. So instead of having actually many use cases for one product to protect, then it's better to focus on one. Let me switch to the next topic, which is multi-party authorization. Authorization means access. Multi-party authorization, or MPA, means involving another person to ensure a proper access decision. Basically, this has benefits for both reliability and security because it helps by having another person take a look at what you're doing. You might actually prevent an error that might result in decreasing your error budget. They might detect through code review, for example, if you're trying to, you or whoever managed to get your credentials are trying to access the code base of the company. And it, of course, provides a level of happiness to your customers, but not from the initial perspective that we were talking about, that they will be continuing to use your product, but from a different perspective. In today's cloud world, customers might actually be more interested in using your product if they know that there's no one person that can access all the data, but that, for example, even your support teams might only be able to access a small amount of data, and they will always require approval from a second person in order to reach it. It's common to ask particularly for multi-party authorization, or MPA, when requesting broad level of access. And here, again, we're talking about risk. You will not use the same levels of MPA requests for all types of actions, but rather those that seem to have a higher risk. You need to figure out who the approvers are and what are they allowed to do? Basically, if all the requests that require a second person to approve them for authorization, all of them say yes, then maybe your organization doesn't allow for approval to say no. So you need to have a culture where it is okay for approvers to deny a request, and they need to have enough context to do so. And here, again, small functional APIs that we were talking about previously are your friend, because the approvers might have more context if you're telling them what you're trying to do for a particular action that you are trying to request. Zero trust. This is a little bit of a deep dive example for networking. Zero trust networking, it means that the user's network location doesn't grant any privileged access. This is something that can be added once there's an extensive automation, where there are safe APIs, and there's a resilient MPA system. So basically, it means that you need to know your users. There needs to be a user inventory. At Google, we've implemented Zero Trust through Beyond Corp that you can read more about in quite a few articles. And in order to start with understanding who our users are, we basically needed to have a look at what jobs do they perform, what type of access are they allowed to have. So there was actually a whole new set of job ladder description that was updated for getting the user inventory. Then you need to know what devices you're dealing with. Were they created by the company? Were they bought by the company? Who uses them? What do they use them for? Then you should build dynamic trust system, the trust infer, where you should pre-compute what level of trust should a user using a particular device have. It's very expensive to compute on the fly this the answer to this request of is a user allowed to access a particular resource from this device. So basically we have agents on each devices that check in regularly and mention this system has all the updates installed. It is currently used by an engineer that has logged in, so they are allowed to access the version control system, for example. So if this information is pre-computed and then regularly updated, this makes it much faster and much scalable to be able to answer the question of what resources can be accessed by what users using what device. And then you need to define a security policy, and this is basically what resources can be accessed by whom, using what. And all of these inputs are going to the access control engine, which then can make a decision. The biggest pitfall that we've seen when implementing Beyond Corp is that inaccurate information about users of devices might result in confusion and badly enforced policies. So the biggest advice that I have here is to start very small, verify the quality of your data, and then slowly scale to new use cases. When talking about security and reliability risk, recovery is an important part that you should take into account. Basically, to be able to recover your system, you need to know what state do you want to recover to. What does a good state that your system has mean? How is it defined? What parameters does it need to have? So basically, returning to the state that your system needs to be in means that you need to be able to sometimes actually bypass some of the protections that you added. We call this break glass. It's a concept that comes from particularly firefighting, when you have the red button that you can break the glass for and reach authorities in case you need help. So you might actually need, in order to perform recovery, you might need break glass mechanisms. Break glass means, for example, bypassing potentially MPA and other protections that your system might have added so that you can actually address security risk. This is a trade-off that you need to make. You want to be able to have a reliable system, so in order for the system to recover from an outage that is in, you might have a security risk. You should be able to audit, which we'll talk about in a second. So performing break glass or bypassing certain protections that you have added in place might be a more complex next step that follows, for example, MPA. You need to make sure that you will audit, because if break glass is used very often, then it might actually become something that your teams are used to using, and then its purpose, the purpose, for example, of MPA will be defeated. So auditing, reviewing all access logs and justifications to make sure they are appropriate. Based on the topic that we previously discussed, small APIs are the basis from which you start. If you have a limited amount of operations that you can perform in order to modify the state of your system, then that is a way to be able to know what action was performed by whom, on what resource, when was that done, and why was that done. You want to detect incorrect authorization usage, for example, and you want to be able to detect this at scale. At Google, we try to have two types of auditing. One auditing is trying to look at, are we using our tools correctly? Do we have the right protections in place? When dealing with the last audit outage, did things get, did it take much longer because we needed to follow additional security measures? And if yes, can we change, for example, that system? So there's a team level auditing that happens, and this helps maintain or increase the usability of the procedures and the tooling that we are implementing. But there's also a second part of auditing, which is done by central security teams. And this is in order to detect breaches, because maybe a more senior engineer or somebody who has seen or who has access to multiple products in the organization might detect something at team level or at a product level. However, they might not detect a widespread action. So for that, we have central security teams that are looking at scaling at scale and try to detect anomalous behavior. We are looking for signals all the time. So there's, with the small functional APIs, with MPA, we monitor for a lot of different signals that are coming in, what actions are done by what actors trying to reach which targets. Here, something that's very helpful is actually business justification. So we use structured justifications. So whenever an engineer or a support person, for example, might require particularly broad access to fix something, then they will provide a justification, a particular bug number, a particular case ID for support, and this can help with the automation and then the additional context that the centralized security teams might require in order to detect anomalous behavior. However, both at the large scale and at the team level auditing, if an auditor is missing context or objective, they might not be able to take an informed decision. And again, from a cultural perspective, one should make sure that in your organization, people are allowed to say no. So to basically wrap up what we were talking about until now, a few key components if we design our system to be able to resist large-scale attack, if we design for this privilege, we should think about classifying functionality according to the level of security risk each functionality holds. We should partition the system through small APIs. And we should use an authentication system for validating user credentials. Here, particularly, do not start from scratch. Really encourage you to use a system that has strong crypto properties that you can integrate with. There needs to be an authorization system enforcing a well-defined policy, and there need to be advanced controls for non-state authorization. The answer to are you allowed to access a resource using this device might not be a simple yes or no. It might be a maybe that might require later additional auditing and checks. These are related to the operational requirements. You should access audit to generate signals. You should continuously test and debug your security policy, and there should be a break glass mechanism to enable recovery. This is going back to the design strategies for managing risk. Basically, if we think about this privilege, then zero trust, MPA, auditing and detection, and recovery are properties that will let you have a more secure system. We talked about the security properties particularly, but if we also think about the reliability properties, they will also have benefits for keeping your customers happy. We talked about zero trust. On the reliability side, we can talk a little bit about zero touch, which is where we're taking the access level one step further, where we want humans to not have access directly to production, for example, but we want them to be able to use tooling that can modify production. So basically that humans are not able to change the state of the system directly. MPA might help in detecting errors that lead to outages. Auditing and detection might have benefits, for example, from a resource consumption perspective. If you want to detect, can I decrease my resource consumption, as in CPU, memory, and so on, then having proper logging from small functional APIs, particularly, can help set different limits and maybe save on costs in terms of what your product is using. And recovery, then if you are able to have break glass mechanisms, then you will be able to potentially fix your system faster. I focused here on least privilege, and I think barely scratched the surface with a few best practices and key components. However, there are many design strategies that you should take into account. Designing for understandability. We're talking about complex systems where many different parts are interacting and having effects on each other. You need to be able to reason about how the different components are, what dependencies they have, how are those kept up to date, what state do they have, and so on. So your system needs to be able to be explained, and you should need to be able to build mental models for that. A way that is helpful in order to design for understandability is to use frameworks, to use best practices, to not start your architecture from scratch, but basically build it on well-known frameworks that can help you reason about how the interaction of the system is happening. Design for a changing landscape. Software is evolving. It's not something that you don't touch a running system. You need to be able to reply to change constantly. There might be different speeds at which you need to modify, for example, your configuration versus your binary. So having often builds, build and deploy often using microservices, using containers will help you adapt to the different speeds of today's modern computing. And designing for resilience. We talked about recovery. Recovery and resilience are interconnected. Resilience means that your system needs to be able to work also when something went wrong. So are you able to offer your users or your customers less performance maybe, even when a system is partly down? We'll not go deeply into these topics. They are just food for thought. Maybe we can discuss them more in the Q&A part, and there can be many, many follow-ups on these. So to wrap up, what I wanted to mention as takeaway for today is that there's numerous trade-offs between security, reliabilities, and feature requirements. So you'll need to think from a business perspective, which of those trade-offs should I make? What keeps my customers happy? And what products and what features and what emergent properties will I add to my products? Basically, security and reliability are very expensive to add after the fact, but there is also price to pay upfront. Generally, that price to pay is lower when designing for security and reliability. Because in today's connected world, can a system be considered reliable if it's not fundamentally secure? And can it be secure if it's always offline and unreliable? Basically, the more trust we put in our systems, the more secure they need to be. And the more we rely on them, the higher reliability do they need to have. Security and reliability are central elements in the architecture of systems, and they should be added from the design phase. And with that, I'd like to open it up to the Q&A. You can learn much more about all of these concepts in 3 books that myself and many of my colleagues from Google have put together in a few books. I'm one of the editors of the Building Secure and Reliable Systems, which was recently published actually also in HTML version that you can find on GitHub. And you can find all 3 books on sre.google/books. Thank you.